Welcome! So in this tutorial we are going to be looking at how we can create a simple ember particle system in Niagara, which is part of what you see in this scene in front of you here. So these particles that are flying around here are part of a very simple system that we're going to be creating, but with a little bit of a twist. We are also going to be creating a blueprint to sort of control parts of this Niagara system, so that it will be cooperating, it will be communicating with it, and therefore we can manipulate this in design time and adjust it a little bit as we need it. So if we take a look at it, we go here and type in Ember, we can see that we have a Fire Ember particle system here, and we have a few parameters exposed. We have motes per cubic meters, we have its dimensions, minimum lifetime and max lifetimes. So all of these things are working together to create a certain density of particles. So if we were to raise the particles over here to 5, which is 10 times as many, you'll see that it's a very high density scene now. Lower it to 0.1, you can see that it's much fewer, and it also depends on the size. It takes in calculations of what kind of a space it is to make sure that this is the amount of motes we have per cubic meters, which is also affected by the average lifetime of the particles themselves. So if we have something like a particle that lives for very long, then we'll have fewer particles spawning because the particles will be staying alive longer, making sure we have the same particle density. If we have something like particles that die off very, very quickly, then it will be compensating with spawning more particles to make sure that the average amount of particles spawned is still going to be this consistent particle density that we have assigned. So that's what we will be creating, and if you want to just jump into the completed particle effect, there will be a link in the description down below, so you can download the project if you want to. It's all up to you. But anyway, if this is of interest, let's check this out. Welcome back. So in this tutorial we're going to be taking a journey together here, actually, because I have decided to delve a little bit deeper into Niagara and learn it a bit better, something I've been wanting to do for a very long time. And as I learn it, I am planning to make some videos so that you can follow along and learn some of the things that I encounter as well. Since this is something that is a learning experience for me as well, if you know any cool tips, tricks, or anything like that that you encounter during the video, feel free to leave those in the comments below and let me know so that I can improve myself as well as the others that are following along. So in this video we are going to be creating a simple ember kind of Niagara effect system, right? We're going to do it with a little bit of a twist. We are going to be making it encapsulated in a blueprint so that we can parameterize some of the aspects of it and have it a little bit scalable for our different needs that we might have, right? So in this case I'm using Unreal Engine 5.3, and we are creating a simple folder, and inside of that we're creating another folder which we will be calling Embers. So inside of this we want to create our Niagara system. So we go to FX and we go to Niagara system, and here we have a few different settings that we can choose. So we can create, for example, copy for an existing system if we have something like that. In our case, we are going to be making a new system from selected emitters, and we're going to be taking something called the hanging particulates. The reason why we're choosing this one is because it sort of has the basics of what we want from an Ember system. So we'll be just tweaking it a little bit. So we'll call it Niagara system Embers, something like that. And we open it up, and so this is what we're encountering to begin with. First off, we'll just select this and call it, instead of hanging particulates, we call it Fire Embers. So this is our emitter then, right? Okay. Other than that, we will also be creating a blueprint. So a blueprint class, an actor, we call it BP_Fire Embers. This will be our container class where we will be having our Ember system inside of, and then having it communicate with the system. Okay, so let's start working on our system. To begin with, we can bring our system into the world here, so we get some sort of representation of what it looks like inside of the world. Opening it up again, we want to get more of an Ember-like feel to this. So starting off, we might want to go into particle update and add a color mode. a color module, sorry, where we can actually set our color for our particles. And in this case, we might want the colors to change over time, because an ember is like fickle and it burns out and such. So what we can do is we can press a little drop down here, and we can say that we want to have a curve, a color from curve, which gives us a curve index, which is in this case will be the age, the lifespan of the particle, and we will have some kind of color going to another kind of color, so the beginning to the end. So in the bottom here we have an opacity, so we go from 1, we go to 0, so that's fully opaque until it's completely translucent, and that seems fine. We can go up here and double click on the starting color over here. The starting color, we can have something that we want to have something that's fairly red. So maybe we take something like a value of 2000 or something like that. That will give it a very emissive glow, as you can see over here now. But we might want to have something that's not just strongly red. We might want to have something that's going a little bit towards the orange as well. So maybe 100, something like that might give us. So you can see here, it's going a little bit more towards orange. Maybe 100 was too much, maybe we want 50. You can tweak with these numbers to get a color that you like, of course. Let's say that this is the color that we want. So that's the color we will be going from, and then we will be going towards another color over here. And over here we can pick a different color, like say maybe something around here. We see the distribution is 1 to 2, 1 to 0.2. So maybe we'll go like 300 and 10, something like that. So the color will change a little bit now from a very intense emissive to a slightly less intense emissive. Again, these are values that you can tweak around with as you want, of course. If we save this and go out in the world, we can now see that this is the result that we currently have with our settings. And this is starting to look a little bit like an ember effect. Next, we might want to actually make it look a little bit like it's actually fire embers, which is, these are two consistent kind of particles right now. So what we can do is we can expand here, and we can go over to our our alpha, and we can say that we want to have our alpha to scale in some way as well. So if we were to open over here, and we can say float from curve from that one, you can see that we get this sort of curve that it's going to go from an alpha of 1 to an alpha of 0. And that might be something that you're after. But if we do something like by pressing middle mouse button along the line, we can add new keyframes like this, you see? And if we were to drag these triangles, we can then edit how these values will change over time. And if we were to make something that looks a little bit like a, that's not what I wanted, like something like that, something that goes up and down, meaning that it will increase and decrease in opacity over time, it will give a sort of flickering sensation. And you can have the opacity going to constant values like 1 and 0, or you can have it vary a little bit. It's completely up to you. Let's say we want to add something that stops at 1 as well, maybe, and like so. So now we can see over here that the particulates, if we save and go out, maybe it's even a little bit more clear. We can see that our particulates are sort of flickering in and out between these different values, right? Which gives it a little bit of an effect of something that's burning out, or possibly flickering around, moving around a little bit in a scene. And the reason I'm creating an ember effect like this is because I want to create something that you can have sort of as an extra layer of intensity for something like, imagine a village, and this village is maybe under attack, or there's fire raging or something like that. You can put these embers that are floating around in the air as well to give it a more atmospheric feeling that this fire is raging and causing a lot of distress for everyone that's involved in the scene, right? So that's essentially what the ember effect is going to be trying to produce. Anyway, so now we have this part done. The next step might be something like, if we look at all of these particulates, they're all looking the same. They're the same size, the same everything. It looks too consistent. Something that we can do then is, if we go in to our system and we go to initializing our particles, we can say that in the case of this one, it's set to that the sprite size is set to random uniform, meaning it's getting a, let's see if I can open this up, a minimum or maximum value like this to get from, which might be something that you're after, of course. But I might want something that's a little bit more random, so I'm gonna be choosing something that's called random non-uniform, which means that the x and y values can be separate. And then you can give some values here, something like, I don't know, I'm gonna try 1, 1, 0, and 0, which means that its size can vary both in width and in height. And this should give us a more random sort of appearance in the different particles that we're having here. You can see that they're looking much different now. So not as uniform as they did previously. Next, we might want to give this system a little bit more life, because it's very static right now. So if we go into our particle spawn, we can actually add something like a velocity. So this will be an initial velocity for when it's actually spawned. And here we can give it a velocity if we want to, but if we want to get a more of a random feel to it, we can instead go to our dropdown for velocity and say that we want to have values in between that we want to vary or randomize in. So if we call range random range vector, yes, that's the one. So now we'll get two different vectors that it will alternate in between. So it will be like the minimum values and the maximum values. So x is in the direction of the field. So if we were to give it something like 100, this means that it will go from having no velocity in the x-axis to 100, and a particle will be given one of these values in the beginning. And then we can have something for y if we wanted to. I'll just leave that one, but I also want my particles to go a little bit upwards. So let's give some of them a little bit of a direction upwards in this case as well. Now if we go and check on the system, we can see that it is moving a little bit, but not a whole lot. To get a better feel of what this is actually going to accomplish, we can go and demonstrate something like this first. If we go to the velocity and we set something like, okay, we want our x values to be 100 and our y values to be 200 or something like that, something a little bit more extreme than what we had, you can see already something's happening over here. But if we go out into the field here, you can see that what's happening here is we have a velocity that's being applied in the beginning, and then you see that it sort of slows down. The reason for this is that we have something called drag applied on this automatically. Here we go, automatic drag. If we were to click the checkbox over here, we can enable or disable this item. You can see that the force is a little bit more constant and violent over here now in the result screen. So that is what's actually contradicting our result right now. So if we do something like add velocity and we go back to setting our values to, I think this is what we had, all right, 20 in Z, something like that. And then we also remove the drag module like so, and then we save and we go out into the third person map. You can see that we now have this initial velocity being applied to our particles, and they are floating around in partly the direction of the system, which is sort of like imitating a wind effect, I suppose. And also we have some slight movement upwards as well. So now it's starting to look a little bit more alive. The sprites are looking a little bit too static and too boring still, in my opinion. So if we go into our system and we go to particle update, we can add something like a rotation. And in this case, we want to have a sprite rotation force because I'm rotating a sprite. And inside of here, we can add some kind of rotation that we want to have. So if we were to take something like 50, we can start to see that they are rotating around now, the smart particulates. You can have something like 150. It depends on how kind of violent you want your rotation to be. Maybe 30 is something that's a little bit subtle and still gives a less boring effect, I think. So now we can see that things are rotating around a little bit, giving it a little bit more life. I'm liking how this is starting to shape up. It is still feeling a bit static because we're giving it an initial force that we are giving the particles to move. But to make it a little bit more random and mix it up a little bit, something that's usually used and is very nice is something called a curl noise. So this can give us a little bit of a random, sort of looking like it's wisping around in the wind kind of a feel. And here you can give some different parameters to affect this. You have a seed which gives it a certain given random output that is consistently deterministic, if that's something that you want to have, and you have some randomization vector that you can apply as well. Usually the noise strength by itself is good enough to get an output that you like. So if I put something like, I don't know, maybe minus 500 to, let's say, 50, you can see that we're starting to swirl around. So these numbers are just like toy around with some numbers that feel that they're intense enough but not too intense, something that fits your effect that you're looking for, right? So in this case, I'm starting to get this kind of wispy, whirly effect now that's going around everywhere here. Although I am liking the life that has been infused into the particles now, I do feel that they're going downwards a little bit too much for my liking, because I want them to act like embers do, which tend to be going up into the air. So what we can do is we go to particle update and we add an acceleration force. So this is a way where we can apply a force that will affect the particle over time. In this case, I want it to go more upwards, so I'll put in some value here, so maybe 200. That should be 2 meters per second of acceleration, I believe. Don't quote me on that. Going up into the map again, we can now see that we're getting a more vibrant swirl effect, but also that the embers are rising into the air, right? So this is looking pretty nice now. Okay, so let's say that this is the system that we're happy with, at least for now. How can we make use of this in something like a blueprint to like parameter? We're gonna run it by parameters. Anyway, so we open up our blueprint Fire Embers, and we start by adding a Niagara system component, like so. We can call it, actually let's call it Fire Embers. And then we choose a Niagara system, and we have a system, and we call it Embers or something like that. There we go, Embers. Okay, so now we have the system inside of this blueprint. We may want to do some things like, for example, change the dimensions of the span, the extent of the system. To have something that's going to be updating as we change variables, we can make use of our construction script. So in this case, we can do something like this. We add a variable and we call this, let's say, box dimensions. And we do it of a vector. The reason we have a vector in this case is because a vector represents 3 different axes. So this will be the size in X, the size in Y, and the size in Z for our purposes. So what we can do is we can get our Fire Embers, and we can say that we want to set a Niagara variable of a vector 3, which is what we have just created, box dimensions over here, and we can say that we want to set this in here, and this will now update. If we change our box dimensions here, we will set the Niagara system to replicate this. But we need to have a variable for us to actually hook this information into, and we might want to have some base values here as well. So in this case, our Niagara system over here is being spawned inside of a shape location, a box plane, and we can see that the box size is of the size 400 400 by 256 in this case. Let's say we want to have that as our default, 256. So this will be our box dimensions. Now we need to go to our Fire Embers, and we need to say we want to communicate this information from somewhere. So we can go to user parameters, or actually user exposed, and go to click the plus, and we can create a new common vector. That should be the 3D space one. So we'll call this the dimensions one. So now we have created a user parameter, and we can say that we want to make use of this user parameter over here. So click the down box here, and we say use. We can type in user because we have a user exposed variable over here. So the user dimensions, if we click that, bam, immediately our system will look very weird because it's generating everything from a single point. The reason because this is happening is because instead of using the values that it had before, it's using the values from this parameter, which is not set. So going to user parameters, you can see that we have 0, 0, 0 set. If we put this back to 400, 400, 256, you can see it goes back to what it looked like before. Okay, so now we actually have a variable inside of our Niagara system we can communicate with, which is dimensions. So going to our variable over here, clicking F2 or just clicking it once should give you the ability to copy paste this variable name. So you can use this variable name over here, like so. And if we now save and go out here, we currently have our Niagara system here, not our actual blueprint. So we'll drag out our blueprint instead next to it. You can see that it is also now producing particles in the same way this one is, but this one now has the variables. We have not exposed these variables. Our box dimensions here need to be set to instance editable, which we can do either by clicking the eye over here or clicking this checkbox. So compiling, saving, running. We now, if we select our blueprint Fire Embers, we can see that we have box dimensions over here. So if we were to say, instead of 400 by 400, we say 100 by 100. Our system is going to be much more narrow in comparison with this one over here. One of the issues you might be noticing is that even though it's smaller, the amount of particles is the same, essentially. It varies a little bit depending on their life sizes, lifetimes and such. So we might want to create a system that's actually taking into consideration that we want to have a certain spawn rate of particles based on the volume that the particle system actually is taking up. So this is what we can make use of our blueprint for here, for example. So we can create maybe a function. Let's call it calculate volume, like so. And inside of here we can take our box dimensions and we can say we want to calculate what is the volume of this in cubic meters, for example. So if we split this, we get our x, y, and z. Now remember, these are dimensions, so these are actually lengths, so they will be positive values. Otherwise, if you're doing something funky and using negative values, you have to absolute the values as well. But we can essentially take our values for x and multiply by the other values, and that way we get our volume. The problem is the dimension is going to be in hundreds, because this is centimeters. A centimeter is the unit of measure for an Unreal unit. So we first actually want to make sure that all of these are divided by 100 or multiplied by 0.01, whichever you want, to make sure that we actually have the length of this box in meters. So this will go from being 400, 400, 256 to be 442.56, right? When we then multiply this, we get our volume in cubic meters, like so. So that means we can return this as a calculated value for us to make use for calculations later on. You can say that this is our volume. That's not how you spell volume. Well, that's how I spell volume, apparently. Like so. Okay, so in our construction script, we could now theoretically call our calculate volume, and we have our volume calculated for other things ahead. Now that we know about the volume that we have, we might want to have a value that represents how many particles we have within this area per volumetric unit, right? So in this case, square meters. Not square meters, cubic meters. So we may want to have something like a variable for this, so an integer. And actually, let's make it a float so we can have the precision of parts even. And we can call this embers per cubic meters, just to be super specific about it. So if we have embers per cubic meters and we multiply this by our volume, then we actually get the number of particles that we would have in total, right? So we could promote this to a variable, and we could call this variable something like total particles at time. Super specific. No possibility of misconstruing or misunderstanding this. So this is the amount of particles that we should have at any point in time then, right? So this might be a good place to start. Now, we don't have any actual ability to influence the Niagara system right now when it comes to the amount of particles that we have. But if we go to the particle system and go to spawn rate, and you hover over this, you can see that this is the number of particles per second to spawn. So let's do like before and create a new variable for us to use. So make a new one, make it common, we'll make it a float, and we'll say spawn particles per second. And then we have a spawn rate of 50 here, so let's make sure that we have that as our default value so that it remains the same to begin with. And then we say that we want to link this to our user parameter that we have, so our user parameter particles per second. So now it's making use of that. That variable is driving how many particles it's actually supposed to be using, and this particle spawn rate we could now actually make use of inside of our blueprint. So let's do like we did before. We'll bring out a reference to our particle system. Then from that, we'll say that we want to set a Niagara variable. And in this case, we were setting a float. Over here. The float name is going to be our spawn particles. We'll go over here, click over here, copy that name, and add it like so. So we're going to be setting our spawn particles per second. So now we just need to calculate this value. So how do we do that? Well, we have our total particles at a time, which is part of the equation, but this also depends on a different value, which is our lifetime of our particles. The longer our lifetime of our particles is, the fewer particles we want to spawn because they linger a lot. But if we have particles with very low lifetimes, they die out a lot, and we need to have a higher spawn rate to keep the amount of particles somewhat consistent over time, right? So in our particles, we have a lifetime. When we initialize them, we have a lifetime min and a lifetime max. So we can just create some new variables for that as well. So we'll create some common variables, and these are floats as well. So we'll say lifetime max. We'll create another one. Lifetime min. So currently they are 5 and 6 respectively. So let's set those values for us to begin with. So min has 5, max has 8. And then we'll go back and hook these up as well, just like we did before. So this is the lifetime min, and this is the lifetime max. So everything should be the same in the particle system because we have the default values as we had before here. But this also allows us now to hook in those values over here. So we'll give ourselves a little bit of space because we will be needing a little bit of calculations done here. like so. So first off, since the lifetime will affect how many particles that we want to have, it makes sense to actually have that as attribute as well for the blueprint system to keep track of, so that it actually updates and keeps on track with our amount of particles and the lifetime and the volume that we have. So let's do what we did before. We'll get our reference and we'll set Niagara variable, and this time we're going to be setting floats again, and we will be setting this variable. We'll promote the actual variable here, and we'll say that this is supposed to be lifetime. Let's go with min first, actually. So lifetime min. We go back to the system, get the name of that variable, pressing F2, copying it, putting it in here. So now we set the lifetime over here. So the default value for this blueprint is not set, so we'll set it to 5 like we had in the other system, so that it's smooth in its transition. And over here we'll do another Niagara float set, like so. Promote this to a variable. And we'll call this one lifetime max. We'll change the name inside here, like so, and we'll compile and set the max value to be 8. So now these are the same as in the system. Now we just need to do our calculation here. So what do we need to calculate? Well, we're going to be having our min and our max lifetimes, so let's take those first. And to get some sort of average in between them, we'll just do that. We'll add these together first. So we'll add them together, and then we'll take that result and divide it by 2. By doing so, we have gotten approximately what the average life size will be for a particle, although this varies. It's not 100% consistent, so it will not be perfect, but it will vary a little bit. But now we have the average lifetime, so to speak. But the total amount of particles at a time divided by the average lifespan should give us the spawn rate that is needed to keep those numbers accurate. I hope that makes sense. Anyway, so if we go to our system over here right now, we can see we have nothing being done over here. It is possible that I have missed a value. We have 8.5 total particles at a time. Embers, this is set to 0, so this is why we're having nothing right now. So if we set this to, I don't know, let's try a value of 2. This means that we should be having approximately 2 particles, 2 embers per cubic meter in the system. So this system over here, we can see that we have, it looks like approximately 1 or 2 or something like that. And if we calculate our volume over here, we have 1 times 1 times 2.5. So we should be having 2.56 particles spawned at any time, essentially. So we can see that it seems to be approximately correct. We're having approximately that amount of particles. This particle system might be disturbing us a little bit from displaying this. So we have a few particles. This might be hard to see, but there are a few particles being spawned here and there. So the calculation seems to be correct, which is good. So what's the point of all of this now then? Well, if we go to our blueprint and we go and we expose the, let's say we expose lifetime min and max, and we expose our embers per cubic meter. Now if we go to the system here and we say that we want to have a system that has 40 embers per cubic meters, that this should be ramping up to approximately 90 or so, maybe 100 particles. Let's say that we expand this to a larger area. We can have something like 500 times 500 times 100. So it's going to be a fairly low height, even though the particles are rising above it. but fairly large area around it when it comes to the width and depth of it. Now, you might be saying, well, it's a little bit difficult to discern where the box of this volume spawning is actually being done. So we could put in some debugging just to show off where that is. So let's create a little function. We can call this something like draw bounds. And this is simply for debugging purposes. It's nothing more essentially. But if we do a draw debug box now, this is where we're going to be drawing the box, and the center location is going to be this actor location. So we'll just hook that up, and the extent is going to be the length of the different axes, and that is going to be exactly what we have for our box dimensions, so that's just fine. And then we can say we want to set it for a duration of 1 second or something, and maybe a different colored outline, like something green. Then if we go back to our code, so in the end here we just call draw bounds. So what's going to happen here, every time that we make a change, we're going to be drawing a outside extended box sphere showing where our system is actually affected. So if we change the value, for example, of number of embers, we'll see that this is the area that is being affected. If we move it around, we can see the area is being drawn where we move it. So we get some kind of indication of what area is actually the spawning area, right? So now we have the ability here to say, we want to have 10 embers per cubic meters. We can control that, fine. We realize that these are living too long, so maybe we want to have 1 to 2 seconds or something like that. Now you can see that since these are living much shorter lifespans, there's a much higher spawn rate to compensate for that. So now we're actually getting that dynamic functionality that we were looking for in the beginning. So now we have a system, we can tweak it with a few parameters, and this of course you can do to any kind of system you want. And this way we can just drop this in some kind of village, and we can tweak the parameters until we get some kind of effect that fits it. And yeah, so I'm gonna be taking some environment that I have probably from some free of the month thing, and I'm going to be dropping this effect into it and see what it looks like. So I'll see you in a moment. So here we have it. I took an environment and I put in a few fires to give it a sense of a village that's being raided or something like that. And I added these embers to it. It lends itself as bringing the situation together as something like there's a lot of burning being done and such. However, there was something that I encountered that I wanted to bring some notice to. So to show that off, I'll take you into the other system. When it comes to the system, if you bring it out and you have something like a really large area, let's say that we have, I don't know, maybe instead of, this is 5 meters times 5 meters times 1 meter, but instead you have something like 5,000, so 50 meters and then 5,000. You can see that you get a very busy kind of effect, right? There's a lot of happening very far in the distance. Now, if we go to the Niagara system here, we can see that on the sprite render, you have something called here, pixel coverage mode. It's what happens when a sprite becomes less than a pixel in size. So in this case, we have these very tiny objects of sprites in the background, and they're shown, especially when I select the system itself, you can see them very clearly because they also get a yellow outline around all the pixels. But if we just show the effect itself, the particle system, you can see that there's a lot of it being done over there. And the reason why it's so prominent is partly because we are using emissives. So even though they're very small over there, they're still lending a lot of presence. If you want to diminish that a little bit, you can go into the system and change it from automatic to disabled. This will make it so that a particle that's very small in the background will not be shown, and it dampens it a little bit when you're getting very far away from them, which might become a little bit overwhelming in a scene like the one I just showed you. Anyway, that is going to be all for now. I hope that this was an interesting experience for you. Hopefully you learned something. I'll be trying to keep doing more of this series moving onwards as I learn new stuff. and hopefully you like it and tag along. Yeah, that's all. Keep on learning. Take care. A big thank you to all of you who like, comment, subscribe and share my videos, or through other means support this channel. You are what makes this channel grow and become a resource for other people to learn from.